So this week, I would like us to see what it means to analyze a circuit. And to be able to analyze a circuit, first we need to know how to simplify a circuit. And why simplifying? Because, hold it in the pen. Okay. Because real circuits in real life are quite complex. They are neither in series, not in parallel. The components are connected in various ways, which are a combination of series and parallel, like this circuit here on the left. It's a combination circuit, and this is another circuit as an example of a more complex circuit, which is, we cannot say that neither of these is either series or parallel. They are not. It's something else. They contain elements of both series and parallel connections. And in order for us to be able to work with them, we need to be able to simplify them. And how do we do that? The first thing to do is to, let us concentrate on this first circuit on the left. The first thing is to identify regions, areas where there are parallel connections, like here. You see this green part. It's a combination, it contains a parallel connection of these two resistors, R2 and R3. So for us to simplify it, the first thing to do is to get rid of this parallel connection. And here at the bottom, I have a series of of different circuits. Each of these is a more simplified version of the previous one. So the first circuit here is actually the given circuit here, this one, the one on the left. The first thing to do is to get rid of this parallel connection. So this resistor is 4 ohms, this is 12 ohms. If we apply the rule of how we calculate the resistance of this parallel connection, we are going to find that these two together, the combination of these two in parallel, give us the value of 3 ohms, the equivalent resistance. This is the equivalent resistance of this parallel connection, and we calculate it to be 3 ohms. I'm not going to calculate it now. So what we do is we redraw this circuit, but instead of this parallel branch, we replace it with a single resistance, which is the equivalent of these two together, the parallel connection. Then what I have here, I have now a circuit which has 3 resistors in series. So what we do are we find the equivalent resistance of these 3 which are in series, and we redraw again the circuit by replacing all these 3 resistances with their equivalent, which in this case is 11 ohms, because 3 plus 3 plus 5 is 11 ohms. So these are the steps that we need to follow whenever we need to simplify a circuit. Start from the parallel connections, identify first of all the parallel connections, then get rid of the parallel connections. And each time we redraw the circuit in a simpler form, with less and less components. So let's see, for example, this circuit on the right-hand side, how we go about. Here it is. Here is the circuit again, the initial configuration of the circuit, and we see we have this parallel connection here and this parallel connection there, 2 of them. So what? So first we find the equivalent of this combination of this parallel connection, 4 ohms each, which means their equivalent is 2 ohms. And the same for this bottom branch, which is also a parallel connection. Their equivalent is 6 ohms and 6 ohms. Their equivalent in parallel is 3 ohms. By the way, if we have 2 resistors in parallel which are equal, say R and R, and these are a parallel, connected in parallel, then the equivalent resistance of those two, it's always half of, has the value of half of either of these resistors. So the equivalent of this is one resistance with resistance of R over 2, half of it. If we have 3 resistors in parallel, but equal resistors, it's nice to know these tricks. If we have 3 equal resistors, all of them are equal, then the equivalent resistance of the 3 of them is the 1/3 of one of these resistances. So the equivalent resistance would be R over 3. So if this way, if we know these little tricks from experience, that it's faster to work some problems if the resistors are equal. Again, if we had 4 equal resistors in parallel, the equivalent would be the resistance over 4, and so on. So, and in general, when we have any resistors of any values in parallel, we know that their equivalent resistance, it's always has a value which is smaller than the smallest resistance in the parallel connection. So this is another way to check if our calculations are correct, because we can do easily a mistake in the parallel connections because we have those ratios. Okay, so anyway, so here the equivalent of those two is 2 ohms. The equivalent of those two is 3 ohms. Here we redraw the circuit with their equivalents. And finally, we redraw the circuit with the equivalent of those two, which are now in series. And so in other words, we redraw the circuit at each and every step by replacing various combinations with their equivalent resistance until we have just one resistance and the initial source. Now, by doing that, if we know the value of our battery, and we find the value of the total resistance in the circuit, we can find the value of the total current in the circuit. And then we can, this is an important information which we can use to find other parameters. But so up to now, the idea is to know that we need to become familiar simplifying a circuit. Here we have a circuit that we don't have anything drawn, so that we are going to redraw it ourselves here. Let's see now. First of all, let me find my values here so that we don't have to do many calculations. Yeah. All right, so let us concentrate in this circuit. How do we simplify it? First of all, we look at it and we try to find where do we have parallel connections. Yes, of course, we have one here, parallel connection with 2 resistors. And also we have another one here with a parallel connection of 3 resistors. So let us get rid of them. So this one first. So to find the parallel, the equivalent of these resistors are 6 and R7. So let's call it the parallel of this connection. It's 1 over 40 ohms plus, plus 1 over 60 ohms, etc. We do the calculations, and if we solve for their equivalent, this is what do I find here? 24 ohms I find here. So this is 24 ohms if we do the calculations, right? So this resistance of the parallel connection on the left is 24 ohms. So we can redraw this circuit now. We start by replacing this complication with its equivalent, which is 24 ohms. And then we have this resistance here, which is 6 ohms. And then there is also another one single here, which is 10 ohms. 10 ohms. And finally, we need to replace this complication here, which is another parallel connection with its equivalent. And let's call this R parallel 2, say. This one, if we do, it's 1 over 50, they are all equal, 15 ohms each, which means the total resistance of this combination is 1/3 of one of them. So it's 15 over 3 ohms, which is 5 ohms. Okay, so this equivalent resistance here is 5 ohms. So in other words, I applied this little trick. If we have 3 equal resistors in parallel, the equivalent is, because they are 3, the equivalent will be the value of 1 divided by 3, which is 5 ohms. Okay, so this is how I found this one. All right, so anyway, from this complex circuit, we simplified it. Now in this, we have the same circuit in this configuration with where there are no parallel branches anymore. But now this can be simplified even further until I have one single resistor. So now all of these 4 resistors are in series, so their equivalent, this will be equal to, let's do the battery here, the equivalent resistance of all these series resistors is 24 plus 6, 30 plus 5, 35, and 10, 45. So this is 45 ohms. 45 ohms. So there we found the equivalent resistance. That is the simplest form of this same circuit, equivalent, of course, to this first circuit. Okay, so I hope you get the idea of how to simplify a circuit. We start from the parallel connections, we get rid of them, and then we see when we are left with just resistors in series, we simplify it even further until we have just one. Now, let us apply all these things in analyzing a circuit. Let's see. Okay, so let us see now. What do we mean by analyzing a circuit? So analyzing series parallel networks of resistors. Series parallel networks means that our circuit has it's complex. It's neither series nor parallel, but it has a combination of both of them. And obviously, in such a circuit, we cannot solve it by just applying one equation, like applying Ohm's law, because it's complex. We need to simplify it. So analyzing a circuit means to know everything there is to know about any device of the circuit in any branch, in any location of the circuit. So for each and every resistor, we need to know what is the current in this resistor, what is, for example, the potential difference across its resistor, across each resistor, the current and the potential difference and the value of the resistance. We need to know, to have this knowledge for each and every resistor or device connected. And also we need to know about the total values, the total voltage across the external circuit and the total current in the circuit and the total resistance. So in other words, we need to know each and every quantity that concerns this circuit. And to do that, it's a good strategy to draw a table like this one. I have drawn it already, where we need to have as many columns as resistors or devices. Here we have 1, 2, 3, 4 resistors. So we have one column for each resistor, 1, 2, 3, 4, and an extra column for all the total values that we are going to include: the total potential difference applied to the external circuit, the total current, which means the current in the main branch, which is the current also in the battery that we have, and the total resistance, which means the equivalent resistance of all the circuit. So you see here the top, what we have, the headings of these columns. Here we're going to include the quantities that concern resistor R1. This is R1 in this case. So R1, its value is given already, 6 ohms. So we can include the values that we already know. So look at this column. It has the voltage, it has a voltage and a current and a resistance. Each column has the same parameters here: voltage, current, resistance. The voltage means the voltage across this resistance, the resistance of R1, 6 ohm. This is the voltage that means. In other words, the voltage and the current correspond to the resistor R1 only. So, and that is why, because there's so many voltages and currents involved, it's good to give symbols to each and every resistor. For example, this resistor is R1, so that all the parameters that have this one index here represent parameters for this resistor R1. So V1, I1, R1. R1 is 6 ohms. We write it there because we know it already. Then for resistor R2, this is resistor R2. We have again the parameters for resistor R2, and we add the value of R2 because we already know. Same for the resistor R3, which is this one, and same for resistor R4. Now for the totals, we have the total voltage supplied to this external circuit. We know it's 12 volts because the problem gives it already. We assume now not internal resistance for simplicity, but would be the same if there was internal resistance. So here is the total voltage, the total current, which means this current here. This is the total current. And the R total, which is all this resistance, the equivalent resistance, which we don't know and we have to find. Now, if we complete this table and we have all those values in place, then we can say that we have analyzed the circuit. And also, one important thing is that in each column, we can apply Ohm's law. So we can apply Ohm's law. Remember what is Ohm's law? R, for example, is V over I, or in whatever form. I equals V over R. It doesn't matter. It's the same thing. So we can apply Ohm's law. Actually, this is Ohm's law. Ohm's law in this form for each and every column. Okay. So if we know 2 out of the 3 parameters in each column, we can find the third one. So it's very useful to know. But the important aspect for now is to understand that we can only apply Ohm's law in one column, vertical column. We cannot mix and match values. We can only apply it with the values in one column. For example, this would be I1 equals V1 over R1. Okay, the same here. That would be I3 corresponding to the 4. This is 4 corresponding to resistor R4 equals V4 divided by R4 and so on. And here for the totals, the I total would be V total divided by the R total. Okay, so we need to be careful how we apply Ohm's law. We need to, every time we apply Ohm's law, we must apply it correctly, in other words. So, and why am I talking about Ohm's law? Because as we go along and we find more and more parameters, unknown parameters, their values, and we replace them in the table, once we have a column with 2 values and one missing value, we can apply Ohm's law and we can find the third value. So, okay, so the first thing to do now, how do we go about? We don't want any complications here, let's make space. The first thing to do is we start from our circuit and we simplify it. We simplify it until we have, the way we saw just now, we start from the complex circuit, the initial circuit, and we find the parallel connections, we get rid of them, and then at every step we redraw it and redraw it until we'll end up with a circuit with just one resistor, the total resistance, and just this simple circuit, in other words, that's the end. So step 1, simplify the circuit. So this circuit here on the left is actually the same, the given circuit. So we start from this connection here, which is the parallel branch, and we redraw all this circuit, but instead of this parallel connection, we have its equivalent resistance. So this is a parallel connection between a 4 ohms and a 12 ohms resistor. If we do the calculations there, the result, if my calculations are correct, should be a 3 ohms resistor. So this resistor, this thing here, actually is the equivalent of this parallel connection. Okay. Now, okay, so we are at this configuration now, which is simplified, more simple than the first one. Now, if we look at this, we see that this branch here is in parallel to this one, but in this branch we have two resistances in series. This 3 ohms resistor and this 3 ohms resistor are in series. So what we do, we add them together and we replace, we redraw the circuit and we replace those two with their equivalent. So I hope you can see that these two here now are in series, and 3 ohms plus 3 ohms is 6 ohms. So we redraw the circuit and we replace these two with the 6 ohm resistance here. Now, we obviously this circuit now is less complex than the previous one. And lastly, we have now these two resistors in parallel, and they're both 6 ohms. This is 6 ohms and 6 ohms. We replace them, you see this parallel branch, we replace it with its equivalent, and since they are both equal, the equivalent is half of the value of 1, so it's 3 ohms. And that is the end of this simplification. And by the way, now that we have that the total resistance is 3 ohms, we can add its value here. We found that this is 3 ohms. What an ugly omega. Let me make a better omega there. So this is 3 ohms. We have the total resistance. And now look at this. We have two values. Look at this column. We have 2 values out of 3. So we can find the third one by applying Ohm's law here. Can we see that? So I total, if we apply Ohm's law, is V total divided by VR total, which is 12 divided by 3. This is volts. This is, and what is this? 12 divided by 3 is 4. So that is the first value. Hold it. Yeah, 4 amperes. So we know that the total current here is 4 amperes. So we already found some good stuff here. All right. Now, let us look again. Do we know anything else, actually? Let us look at this initial circuit, which is the same like this one. We know that this the battery supplies a potential difference of 12 volts in the external circuit, which means the potential difference across these 2 points is also 12 volts, isn't it? If we were to connect a voltmeter across the resistor R1, that should also read 12 volts, isn't it? 12 volts, which means we actually know the potential difference across the resistor R1. So we can add this value in the data for R1. Here is R1. The V1, in other words, is 12 volts. Okay, 12 volts, because this is the potential difference across the resistor R1, which is the same as the potential difference supplied by the source, isn't it? Right. So if we look at this column now, we have 2 values out of the 3. We can find the third one. So if we apply Ohm's law in the first column, that would be V1 divided by R1. This will be 12 divided by 6, and this is 2 amperes. We have another value, 2 amperes. So we know whatever we need to know about resistor R1, 2 amperes. That's interesting, because now we know that this the current in resistor R1 is 2 amperes. If I wonder if I can do all of it here, because in the next page we don't have this diagram. Yeah. All right, so this I1 now is 2 amperes. So the current in the resistor R1 is 2 amperes. And if this current is 2 amperes and the total current is 4 amperes, look at this total current is 4 amperes. And this current is 2 amperes. Obviously the current in this branch, is also 2 amperes, isn't it? because 2 amperes here and 2 amperes there make up the total current, which is 4 amperes. So look at this now. We have 2 amperes, 2 amperes. That means the current in resistor R4 is also 2 amperes. So the current in resistor 4 is 2 amperes. Now that we know 2 out of 3, we can find the potential difference across resistor 4, this potential difference. So again, applying here Ohm's law, I4 equals V4 divided by R4. V4, sorry, what am I saying? We are trying to find the V4, yeah. V4 is actually I4 times R4, and I4 is 2 ampere, 2 amperes, and the R4 is 3 ohms. So 2 times 3 is 6 volts. Okay, so there we have we found that this potential difference across R4 is 6 volts. All right, so 6 volts. We have we know all these values. Great. Now, okay. So from here, in other words, if we had the voltmeter here, it would read 6 volts. Okay, across the resistor R4. Now, if we know that this potential difference is 6 volts, and we also know that this potential difference across the resistor R1 is 12, obviously, the potential difference across this branch would also be 6, isn't it? If we had the voltmeter here, it would read the remaining voltage as 6 volts, because 6 volts plus 6 volts altogether make for 12 volts altogether, isn't it? So we have, so I mean, if I draw this part with this resistance R1, and then I have these other 2 parts here, maybe we said the voltage across this resistor is 6 volts, 6 volts. Obviously, since this is 12 volts from there up to there across R1, and this is 6 volts, obviously this must also be 6 volts, isn't it? That is why I have a 6 volt there. Okay, across. Now, I hope you understand where this 6 volts comes from, in other words. Okay, I don't want any special extra noise here. All right. So what else did we find here? We have the R4 complete. The R1 is complete. Yeah, now we need to complete the data, the parameters of these 2 resistors which are in the parallel connection. So we just know up to now, we just know that the potential difference we found across this parallel connection from there up to there is 6 volts. All right. Now it's time to look again at our simplified diagrams here. And what we have here, we found that we said that this from there up to there is 6 volts, and from there up to there is also 6 volts. Okay, so which means now, if from there, if I move backwards to the previous diagram, which was the original diagram, we have that the voltage across the ends of this parallel branch is 6 volts from there up to there. Now that we know that the voltage from there up to there is 6 volts, and we know the resistance of each of these resistors, first of all, 6 volts will be the voltage across resistor R2, this is R2, and also it will be the voltage across resistor R3, because they are in parallel. The voltage across the ends is the same. So we can write this voltage in our table. Where is R2? The voltage is 6 volts across R2 is 6, not yes, 6 volts, and also the voltage across V3 is also 6 volts because they are in parallel and the voltage across their end is the same. And now you can see that we can find the currents in these resistors R2 and R3. Again, applying Ohm's law, let's for column R2, sorry, for the column of the R2 resistor, the current I2 is V2 divided by R2. V2 is 6 volts divided by the resistance, which is 4 ohms. Oh, and it's 12 o'clock. Sorry. Sorry, guys. Okay. Okay. We need to stop because this is, anyway, let me tell you what I find here. This is 1,5 amperes, and this is also 0,5 amperes. If I do the same here, and maybe we should continue next week now because time has gone. And I hope you understand roughly the idea of what does it mean to analyze a circuit. Now the table is complete, everything is known. Everything that we need to know about this circuit is known. Okay,